We're going to start the course by looking at integration using Chapter 16 of the textbook Mathematics for Economists. The term anti-differentiation is often used in the context of integration, but I prefer the term integration over the term anti-differentiation. Now, it's very easy to figure out how to do an integral, theoretically at least. Suppose we have a function f of x is equal to x squared. We know that the derivative of that function is 2x. And if we take the derivative of the integral of that derivative, and we write it this way, without any beginning and ending points, we have an indefinite integral. And if we use 2x as our function here, then we know that the integral of it is x squared, but because it's an indefinite integral, we also have to add this constant c, because you know that if you take the derivative of x squared plus c, it's 2x. So you have to take into account this c, which is known as the constant of integration. Now there are some rules for integration. There's the power rule, which says that if you integrate over a function x of n, then you get 1 over n plus 1 times x to the power n plus 1 plus this constant. And of course, you have to have that n cannot be -1, otherwise you'd have a 0 here. The integral of a sum is simply the integral of the separate functions. So we have an integral of f of x plus or minus g of x, and then taken by d of x, we get the integral of f of x d of x plus or minus the integral of g of x. The integral of a constant multiple is simply equal to, we can take that k, that constant, and put it outside the integrand sign, and we get that k, the integral of kf of x is the same as k times the integral of f of x. We also have an exponential rule. The integral of e of x dx is equal to e of x plus, of course, this constant, because we have an indefinite integral. We have a logarithmic rule that the integral of 1 over x is simply log of x plus, again, this integration constant, as long as x is greater than 0. Because if it's less than 0, you can't take the log of it, and if it's 0, we can't divide here. Okay, so some examples. The integral of x cubed is simply 1/4 x to the 4th plus the c. The integral of x squared plus x5 is simply equal to the integral of x squared, which is x cubed over 3, plus the integral of x to the 5, which is x to the power 6 over 6, and again this constant. 3, the integral of 12x cubed, we can bring the 12 on the outside here, and we get 12 times the integral of x cubed, and we get that it's 12 times x to the power 4 over 4 plus c, and that gives us 3x to the power 4 plus that c. The integral of e to the f of x. So let's first take the derivative of e to f of x with respect to dx, and that gives us f prime of x e to the f of x. And if we take the integral of f prime of x, the first derivative of f with respect to x, multiplied by e to the power f of x, we then get back e to the power f of x plus the integration constant. The derivative of the log of f of x is simply f prime of x over f of x, and the integration, if we integrate that f prime of x over f of x, we get that the log of f of x back. And we'll see that again a little later on, how we do that. So now we can look at the definite integral, and that's the Riemann integral. And what it says is that we look at the area under a curve. We're going to take a simple linear function here, 2 of x. So we have 1 on the x-axis, and 2 is the equivalent for f1 is 2 times 1 is 2 on the vertical axis. And this is the area that we're interested in calculating. So now we've got a definite integral, and we want to know what the shaded area is going to be. So we take the integral from 0 to 1 of this function f of x, which is the integral from 0 to 1 of 2x dx, and that's equal to x squared. And it's evaluated at 1 and 0. So we plug the 1 into the x squared, and we get 1 squared, and we then subtract 0 squared, and we end up with an area of 1. And you can see that because the area of a triangle is given by 1/2 the base times the height. So 1/2 of 1 times 2 is equal to 1. Now, what the Riemann integral does is it breaks up any interval into very small little intervals, and then calculates the area under each of these little segments. Now, it depends on how you calculate that area. In one case, we're leaving these little blank triangles. We don't count that. In the other case, and is the upper sum, where we actually truncate that at the top. So we include these shaded triangles here, and these result in an upper sum that's going to be higher than this lower sum by the amount of these little rectangles at the top. Okay, that's the difference here because of these, the way we've truncated here versus here. So the upper sum is greater than the lower sum, and in this case we've divided our area into n equals 6 segments, and our question is what happens as n approaches infinity. So as you have an infinite number of segments between 0 and 1 rather than just the 6 we're using. And I think the text is using 5 or 10 or something like that to make it somewhat simpler. And they actually calculate the areas in each case. But in our case, what we're saying is that as n approaches infinity, then the upper sum of these areas, so this is the upper sum here, is going to equal the limit of n approaching to infinity of the lower sums. And that will then equal 1. So a fundamental theorem of integral calculus is that if we let f of x be a continuous function on a closed interval a, b, and we let large f, capital F of x, be the indefinite integral of f of x, then we find that if we integrate between a and b over the function f of x dx, it's equal to the integral, or sometimes it's called that antiderivative, of capital F of x evaluated at b and subtracting a. So we evaluate that large F at b and subtract the value at a. Note, with a definite integral, we do not have that integration constant anymore. So now if we go back to our original problem here where f of x is equal to 2x, and instead of saying 1, we just make it b, and as a result we get 2b on the vertical axes here. And we know that the area is 1/2 times the base times the height, so it's 1/2 b times 2b, which is b squared. And we can do this by integrating from 0 to b over the function 2 of x, which gives us, once we integrate it, it's x squared evaluated at b minus x squared evaluated at 0, which gives us b squared minus 0 squared, which is simply b squared. Now consider a second example, which is a bit more complicated. Find the area under the function h of x, where h of x is equal to x cubed plus e to the power x times 3x squared plus e to the power x. Now the first thing you should note is that if you take this first term and you take the derivative of it, you get exactly the second term. So 3x squared plus e to the x. In this case, what we want to do is integrate between x equals 0 and x equals 1, which was b equal to 1, but our function is going to be different than simply 2 of x. So to integrate the above function, we use what's called the substitution rule of integration, and we'll come back to that on page 623. So the substitution rule of integration says that if you have a function, an antiderivative function, function u, is where the derivative of that function with respect to u is equal to f of u, lowercase f, and u is given as a function of x, g of x, then if we integrate the lowercase f of u, du dx times dx, so in other words, we're basically going the integral of f of u times du, or if we go f, substituting that u in here, we get g of x times g prime of x dx is simply equal to fu plus c. So that means that to find the integral of this function, all we do is we set x cubed plus e of x, so x cubed plus e of x equal to u, and we know that du dx is 3x squared plus ex, and thus f of u is simply equal to u. So substituting that in, we get, again, using this formula, we get f as a function of u times du over dx times dx is simply equal to the integral of u du, and that's equal to u squared over 2 plus c. Remember, we've got an indefinite integral here, and that then translates into x cubed plus e of x plus 3x squared plus e to the power x. When we integrate that function, we get x cubed plus e of x squared, so this u squared, here's our u, and this is squared, over 2 plus c. So we get this function here where u squared over 2 is our x cubed plus e of x squared over 2. So then we get the definite integral from 0 to 1 is simply equal to this original function h of x, and we've solved it now over here, and we're going to plug in 1 and 0. So we're going to go 1 cubed plus e to the 1, square that, and divide by 2, and then plug in the 0 and do the same thing. So we get 1/2, there's our half, 1 cubed plus e to the 1, which is about 2.7 something, and then we get minus 0 cubed, which is 0, and then e to the 0 is 1. So we get this number here, that number, divide by 2, and we get 6.4128099 as this area between 0 and 1 for that function. So that's the area underneath that function. So now, as an example, consider a stock of capital and a stream of investments that increase the capital stock. We can use the area under the investment curve, if we know it, to measure the change or addition in the capital stock between two periods. So here's our problem in outline. We have some function I of t, which is our investment function, the amount we invest in every time period, and we want to know what the effect is of the on the capital stock between time period A and time period B. So this is our delta t. This shaded area here is our change in the capital stock. So we can write that as the change in capital is equal to the capital at time t plus delta t. So this is our TA, and our delta t is the difference A to B, minus what the capital stock was at A, divided by delta t. And we take the limit as delta t approaches to 0. So here is where we're taking this particular case where we're taking those, what do we want to call them, those slivers, if you like, underneath the function. And what we're doing is we're making them extremely small by setting the change in time approaching 0. And what we get then is dk over dt, which is simply our investment. So delta K then is equal to KB minus KA. So it's the area, or pardon me, the capital stock at B minus the capital stock at A, and that's given by the integral between A and B of this particular function. So it's the area under that function that we're interested in. So a theorem is that if f is continuous over the closed interval AB, then for any x that's an element of that closed interval AB, the integrand is given by the integral from a to x, where x is somewhere inside that AB, of fk dk, and that's the Riemann or definite integral of lowercase f of x. So notice here that k is an integrand dummy variable to avoid confusion with the upper variable here on the integration sign. So if we look at that, we get the integral from a to b of lowercase f of x is equal to the integral of a to b of f of x dx plus c minus c is equal to the integrated function, the antiderivative function, if you like, evaluated at b minus that function evaluated at a. And in the above investment example, we had that k at any period of time was equal to the integral between t at time 0 to t of that investment function dx. So at some starting time t, if we go back to this diagram, it would be over here somewhere, perhaps 0. That would be our t of 0. The investment function I of x dx with the first derivative of the capital stock at any given time equal to the investment at that particular time. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.